All right, how's it going, everybody? We are gonna look at our kind of first, well, this is not really our first typical lecture right here. We're still looking at a bit of kind of review topics for 5.1, 5.2, and 5.3. I do think that I have covered a lot of the sort of reminder and practice ideas associated with 5.1, 5.2, 5.3 in my refresher assignment and video. I think that's going to help us out with a lot of our doing. So the purpose of this video is really to iron out a few concepts that are associated with 5.1, 5.2, 5.3 rather than kind of the doing parts of 5.1, 5.2, and 5.3 that I expect you to be able to work through on your own. This is sort of for the purpose of me highlighting the most important concepts here. My experience in general in calculus is that people tend to underestimate the importance of Riemann sums. Basically, that's kind of maybe going to be like the focus of this video. Basically, today is to try to convince you that these things matter and that they're going to make your life way better in the next coming weeks rather than worse. And maybe my one little modifier to that statement should be Riemann sums, okay, maybe are still like not actually our friend because dealing with summations is very difficult, but the concept of Riemann sums and Riemann diagrams is going to be very important. So that's really good news for you because dealing with the sums usually is difficult, but drawing the diagrams is incredibly helpful. And so that's kind of going to be one of our kind of focuses here today. So in a sense, this is our review of 5.1, 5.2, 5.3. I'm not going to hit every topic that are in these things here. I'm going to kind of try to be sparing here. If anybody is in chat and would like to, if we have any specific questions about some things that you're a little stuck on in here, you're certainly welcome to ask that. But otherwise, I've got kind of a spread of some things that I want to kind of work through here. And it's not too much, but I'd kind of like to talk in depth about a few small things rather than try and talk about each individual little idea that's in these kind of leading up sections right here. So we're going to start by doing some area approximating here with our Riemann sums. And as you can see with what's up on the screen right here, we're going to make an approximation with a Riemann sum using the L4 approximation. We are going to use a Riemann sum then to, instead of finding an approximation, find an exact area. And then we're going to use a definite integral to find that same exact area. So you should notice in number one, we're doing an approximation to, or sorry, part A, we're doing an approximation. Parts B and C, we're looking for exact area. We certainly expect our answers for B and C to be exactly the same. And we expect them to be vaguely close to part A, but hopefully all of you know by now that if we're doing a Riemann approximation with only 4 rectangles, we don't necessarily expect it to be a very good Riemann approximation here. So in fact, A will probably end up being kind of far off from our actual answer here, but it's a bad approximation because we only got 4 rectangles. So let's go ahead and take a look at this. And I have set myself up to draw a couple of diagrams here to get started. And I want you to notice right away that I want to distinguish between my Riemann diagrams for my like L and R sum approximations versus my generic or general Riemann diagram. The specific L4s and R4s, those are good if we want to do approximations. To be honest, I'm not really interested in doing lots of approximations this semester. They are really useful. There's so much integration that can't be done that approximations really matter in life. But I am, because this semester is a bit more about integration techniques rather than what do you do if you can't integrate, I am really interested in us thinking about some more generic Riemann diagrams that aren't specific to things like this being L instead of R, this being 4 instead of any other number. That's kind of specific. So I want us to think about how do we draw really generic diagrams that are still really useful to us. And I'm going to really try and highlight very exactly why I think these generic Riemann diagrams are so helpful for us. Once we've gotten through A, B, and C right here. So let's go ahead and draw this L4 Riemann diagram. So a couple things that we're seeing here. We're trying to approximate the area under the curve y equals x squared. We know that's a parabola. One of the things that we often leave off when we verbalize this is that if the area underneath a parabola is infinite, right? Because parabolas, you could just go down forever. In general, we're always referencing the area between a curve and the x-axis. It's rarely mentioned, but that's always the implication here, is that we're looking for, when we say the area under a curve, we mean under the curve but to the x-axis. So if I'm looking at drawing my approximating idea right here, I know that I'm looking at the interval from 0 to 1. And so, oh man, it's the best looking diagram you guys are going to get all semester. So there's my point that I think is sitting there at 1, 1. That should be at an x value of 1 here. I know this is also at a y value of 1. That's actually like a square right there. Some other values of interest to us. We know that we're looking for an L4 approximation. That means I'd like to break this down into 4 subintervals. Since our width of each of these subintervals here, we can tell that this is going to be, our delta x should be b minus a over n. In this case, b minus a is 1 minus 0. It's our upper bound minus our lower bound. N is our number of subdivisions. It's 4. And so we can clearly see here that we are going to get a width of 1/4 for each of those. That wasn't nothing surprising here right there, but if you want to be able to do the computation for more difficult examples, we certainly can. So some other things I'm going to do for myself in general when I work with Riemann sums, I try and avoid doing things like reducing these fractions because obviously, or not obviously, it typically ends up being the case that we want to like deal with these fractions as a group, and so all of them having that common denominator of 4 is actually probably in my best interest here rather than writing that guy as a 1/2 right there. And certainly we've got this guy at 0. So one thing I want to do before I move away from this diagram is help us remember that whenever we're doing our L4s and our R4s and our stuff like that, in this case, for example, this is an L4 diagram, but very importantly, notice that there are 5 points that are indicated on my diagram right here. When we're looking at L4 and R4, it matters that we pick out which 4 of the 5 are the ones that we are interested in. In this example here, so I'm not quite done with my diagram yet. In this example here, since we are doing L4, I know that I want the left corners of my rectangle to be the parts that intersect each of these dots. So here, I want this dot to be the left corner of a rectangle. I don't even have to draw the rectangles in order. I want that to be a left corner of a rectangle. There we go, now it is. And I can do this for all of my rectangles. So here's my L4 diagram. And again, the thing I want to remind you guys is this diagram is very specific to this being L instead of R. This diagram is very specific to this being 4 instead of any other number of subdivisions. And we would like to come up with more generic diagrams than that. While I was talking there, hopefully the thing you saw me doing was filling in my dark line on the x-axis right there, because we do in fact have a rectangle of height 0 right there. It is intersecting with that point that is sitting there at the origin. Right? So if we want to now talk about our L4 approximation under the curve, we are literally just adding up the areas, those 4 rectangles. Here we can see that because this function was strictly increasing over the interval 0 to 1, the L approximation is an under approximation. If this was a decreasing function from 0 to 1, then the L's would give an over approximation. We can make the exact converse statements for our right-hand sums. If it is an increasing function, the right-hand sums will be overestimates. If it is a decreasing function, their right-hand sums will be underestimates. A quick couple pictures can kind of justify all those guys for you right there. So I'm expecting that whatever answer I get for this is going to be slightly less than the exact answer that I'm going to get over here. And our L4 approximation, we just want to remember that when we're coming up with our area approximation here, that this is approximately equal to the sum of all the widths times the heights. That's my most generic way I can possibly say this, right? Now, the nice thing for us here is that all of the widths are constant. They're all 1/4. The width is really delta x right here, right? This is w equals delta x. The width is the change in x that we experience. And so since the width is a constant of 1/4, this constant can be moved outside of the sum. So I'm going to write this now as 1/4. 1/4 is the width. But it's really just times the sum of the heights now, because all those widths were going to be the same. I factored out that same width from each of those guys. So all I've got to do is come up with each of my heights, and we will just do our little bit of computation here. So 1/4, my first height is 0. And I know that it's 0 because the x value that I chose to help me be the determiner here was 0, and 0 squared, because we're looking at the function y equals x squared, is going to be 0 squared. Right? For the next one here, we are at an x value of 1/4, so therefore the height on our curve should be 1/4 squared. And we can keep on walking down the line, 2/4 squared, and we've got 3/4 squared. Very importantly, we're noticing because this is an L approximation, we ended 1 point before the end of our endpoint out there of 1. If this was the R4 approximation, we would have instead discluded our leftmost endpoint. L's discard the rightmost, R's discard the leftmost out there. There's always one more point than we have subdivisions here. 5 points for 4 subdivisions. So it looks like we just got to add these guys up. I'm seeing here 1/4 of, and what are we getting here? We got 1/16 plus 4/16 plus 9/16. That's going to give me 13, 14/16. 14/16, 1/4, 14/16. I don't know, a little simplification here. I guess that's 7 and a 2, so 7/32. So again, this is our approximation. This is not our exactly correct answer. We know that we're going to expect our actual answer to be slightly larger than this because we can see the chunks of area that we've missed in here that we didn't exactly get for ourselves here. And maybe the one other thing I feel I kind of should go here that I kind of wish I would have written here is, again, identify in this case here when we're doing our L's and our R's, is we found our X list here of points of interest to be 0, 1/4, 2/4, 2/4, 3/4, and 4/4. Those were all the points that we found, right? Those are our 5 X values that are indicated over here. What we did is that we decided that if we're doing our L4 sum, then those are the 4 endpoints that we use. And we saw that if we're going to do our R4 sum, we're using the right 4 endpoints. So there's our R4 sum terms as the right 4 out of the grouping right there. So there's always going to be one more endpoint than subinterval. And for the L's and R's, we just exclude one of our subintervals right there. So we got our approximation for our L4 area. The nice things about our Riemann sums, we're always going to have this constant width. So this width can always be factored out of the sum as a constant right there. So the W was 1/4 and I moved it to the side. So we really just had to add up all of our heights right there to make it happen. So the question that we should ask now is, how do we upgrade this? How do we say, okay, so that was just an estimate right there. We'd actually like to get the exact thing. Well, the idea here is that since we are in calculus class, we should know that the answer somehow involves infinity. The way that I can do this smarter is I could use more rectangles. How many more rectangles? Let's use an infinite number of rectangles. So I was pretty bad with my notation right here, by the way, and I was bad here on purpose. I didn't notate this sum with any of our proper notation here, but I'm going to do better on that one right here. So let's write some better notation for this, and let's step up our Riemann sum to actually get the entire exact area here. So now what I'd like to do instead is say I still want to be adding up a bunch of widths times heights. It's still going to be the case that all those widths are going to be the exact same amount and that I'm going to be able to factor that term out. But now I want to think of this as breaking this guy down. Instead of into 4 rectangles, I'm going to say, let's let our I go from 0 to n. And how many subdivisions do we want? If before we had n equals 4 subdivisions, I would now like to have n go off to infinity. So I'm going to now take a limit as n goes to infinity to say, let's get as many subdivisions as we can get, an infinite number of subdivisions. So now we're taking all this interval from 0 to 1 and we're dividing it up into n parts. We're going to let n go off to infinity, but we don't need to worry about that limit for right now. We're just subdividing this into n different subintervals. So the first question I would ask is, how wide is each subinterval if we've divided up into n parts? Well, W here, which is the same thing as my delta x, we're still just going from a lower bound of 0 to an upper bound of 1, but we're now subdividing into n parts. So it looks like the width of each of my rectangles now is going to be 1 over n. So that is going to be, so let me get my limit here. Limit is n goes to infinity. Now, 1 over n is the same as the width. And since this n doesn't depend on which of our terms that we're at, notice that I is our indexing variable in our sum. There's no i's in this statement right here. The width is just always 1 over n. So since there's no i's in the width statement, that can be factored out front. The heights do depend on which one we're looking at. If we go further out in our rectangles, we're going to get taller rectangles. So the heights should depend on which I we're at here. So what I'm going to say here is this is my limit of all of the widths are 1 over n. What I now need to come up with is a state of what are all of my heights. Well, a couple things that we hopefully remember here is this. One, when we're doing our approximations, it matters if we do our L4s or our R4s so that we know if we're going to get over or under approximations. In this case, I'm going to get my exact answer anyway, so I really don't care if I start from the idea of an Ln or an Rn approximation. They're both going to converge when n is taken to infinity on the exact answer. So left and right sums aren't really significant to me. All I want to do is think back to my Riemann diagram that I made right here and think about how we broke this down. This diagram was broken down into 4 subintervals, so each one had a width of 1/4. This one's being broken down into n subintervals, so each one has a width of 1 over n. So if the first one was at a x value of 0, if we were thinking about this as our L approximation that we're making infinitely good, then our first height should be at 0 squared. Our next height should be at, instead of 1 over 4, should be at 1 over n is our next value of interest. If we've broken this up into n subintervals from 0 to 1, then 1 over n is our second x value. And so 1 over n squared is the height of our next value. Remember here we're squaring specifically because we're looking at the function y equals x squared. That is particular to the function of interest that we are looking for the area of interest underneath. My next one then would be another 1 over n units away, so 2 over n. And we're going to do this how far? Well, we want to do this until we get to our final x value, where our final x value is just 1, right? 1 is also thought of here as n over n. Once you've done n subdivisions that were all n wide, then here I could maybe just think of this as n over n squared, right? So that's all of our heights. If we broke this up into n subintervals, then we should get n components here that are going to have widths of 1 over n, heights of their appropriate x value squared. What we've got to be able to do now is we've got to be able to, unfortunately, compute this sum right here. And this is immediately where we should say to ourselves, computing Riemann sums is obnoxious. Using ideas of Riemann terms is going to be really helpful. And again, we're getting to that. We're doing our annoying Riemann sum first. We're going to use Riemann diagrams to be helpful for us in a second here. So here's the things I'm seeing. 1, all of these terms have an n squared in the denominator. This term has a single n in the denominator. So what I'm going to do is I'm going to factor out the division by n squared from all of these terms to leave us with a 1 over n cubed here. We'll just have all of our numerators left over then in this grouping out here. So we can look at limit as n goes to infinity of, I've got 1 over n cubed because I'm factoring out the n squared denominator from everything. And this is 0 squared plus 1 squared plus 2 squared plus all the way out to n squared. So if I knew what the sum of the squares of the first n integers were, then we'd be good to go. This is one of those things where maybe you do, maybe you don't. If you don't, then you can go to Wikipedia and you can say, wiki sum of integer squares, and this formula will pop up for you immediately. And you should immediately be saying to yourself, though, well, this is dumb. If I have to go to Wikipedia to look up a formula all the time, then how is this helpful to me? And I agree with you. Doing Riemann sums is hard, but Riemann ideas are important. So we want to keep sticking with these here. So what you're going to find is that this is going to be equal to the sum, or excuse me, this is the same thing as the sum from I equals 0 to n of I squared, right? This is me rewriting this term as a sum now. This is saying I'm adding up an integer squared, starting from the integer 0, going up through the integer n. And this has a formula for it, as I just said. If you look up the sum of squares formula, this is one of those things that's on the fringe of things that I've memorized. I always kind of forget the exact details of this, but this should be, I think, n times n plus 1 times 2n plus 1. Over 6. And actually, here's what I'll even do right now. I mean, I think I wrote this down, but I don't even care. And I want to show you guys why I don't even care. That is what I've got written down here. All right. So I get the thing that I'm remembering is this. Very, very honestly, I might be actually like dropping a negative out here, and I want to show you that I really don't care if I am. I feel like this might be like a 2n minus 1 or something like that. Doesn't even matter for us right here. Here's what's going to happen. The reason why not is because this limit is really going to tell us all of the information that we actually need to know right here. So notice here that if I were to multiply out all these terms in the numerator, I'm going to get a 2n cubed. I'm going to get some other terms. I'm going to get a squared term. I'm going to get a linear term. I'm going to get a constant term. But when n goes to infinity, none of them are going to matter compared to the cubed term. So here's maybe my like lazy mathematician's way of writing the remainder of this statement. The reason I'm writing it this way is because I don't care if that's a plus a 1 trillion n squared. The point is that the n cubed term will be dominant. The n cubed term is going to go ahead and interact with my divisor or dividing term of n cubed here, and it should be just leaving us with this statement now that just says all these terms are going to be insignificant when this n is going off to infinity here because of this divided by n cubed, and it looks to me like we're just going to be getting 2/6 or 1/3 for our answer right here. And so we should notice, by the way, coming back to our last answer here, 1/3 here might be like 7/21. This is less than that. This is less than a third, and we were expecting an underestimate. So I do agree with the fact that this answer was an underestimate here. And so I do want to kind of go back and like talk about some of the stuff that happened right here. One, I had to look up this formula to go from the sum of the integers squared to this formula right here. That's dumb. If we have to go like look up summation formulas all semester, then what good are Riemann sums, right? The other thing that's kind of dumb here is I don't even know if I actually got the entirety of this formula right. The only thing that I know is that this formula, when expanded, has a 2n cubed on top. And so this n cubed canceled with this n cubed. This n cubed divided away any of the smaller powers of n that were sitting out here, leaving us just with our leading matching coefficients of 2/6 when I evaluated that limit as we go off to infinity right there. So we're landing at this exact answer of 1/3. So like on the one hand, it's like, cool, we could do this. On the other hand, it's like, we had to look some stuff up and like we don't even know about some of the parts in there. But we got to a good correct answer right here. And so I'm going to keep on saying this. Doing Riemann sums, oh my gosh, I got to flip my camera horizontally. Doing the Riemann sum, a little annoying, often involves you having to compute sums you don't know. Thinking in terms of Riemann sums, outrageously useful. And if you can't do it, there's going to be entire sections unaccessible to you this semester. So that's where we're going to get to in a part D here in a moment. So what we want to do is use the simpler techniques that we found, right? Because this is a crap load of work for us to figure out that 1/3 is the area underneath x squared from 0 to 1. There should be easier ways to do this. So where we also wrapped up our last semester with was getting some definite integrals here. So here, the way that I would notate this guy is like this. Some very important things. One, our variable of interest is describing x values. X values of interest means that we are integrating with respect to x. And this is similar to derivation. You can't just say, what's the derivative of this function? It matters that you say, what's the derivative of this function with respect to a given variable? Same exact thing with integration. We want to track that. And in fact, I'm going to switch it on you in a bit here, so it does matter. In this case, we are going to this interval 0 to 1. I am implying our x values. And so we're integrating over x, right? So what we want to know is, how do we compute this? Well, I'm going to scroll back up real quick here. I know I'm going a little out of order in here, but I want to come back to this picture that I never drew, this general Riemann diagram for our exact integral, and I guess I'll just draw it down here with this problem. I want to use a general diagram to help me out here rather than that specific one that we drew for L4. So here's the diagram that I'm actually really picturing for myself right here. What I don't know is, are we doing L's and R's? What I don't know is how many things are we subdividing this thing up into? What I do know is what my curve looks like, and I do know what the bounds are, 0 to 1. So what I'm going to do is I'm going to draw the most generic Riemann picture that I can draw for myself. I know that all a Riemann sum is adding up a bunch of sticks. When it's a finite sum, when we're actually doing things like L4, those sticks are actually whole two-dimensional blocks. It's a whole two-dimensional area for each rectangle. When we let the number of blocks go to infinity, their width becomes infinitely thin, and a rectangle with infinitely thin dimension in one dimension is really just a line, right? It's just a stick. It's literally like a one vertical line right there, right? So all I want to do is I'm just going to draw for myself one generic representative Riemann stick. And there it is. There's my entire diagram. This is the width, delta x, and this stick has a height of f of delta x, right? In this case right here, that'll be a squared term right there. The reason that this helps me is because this tells me every single term that I need for the integral that's going to be associated with doing this. What this tells me here is this. I know that I am adding up, I am summing. That is literally an integral symbol that looks like an S. The S stands for summation. We are adding up a bunch of rectangles. All I need to do is describe the width and the height of each of the rectangles. Well, the height of each of the rectangles is going to be x squared at any given location because this formula is y equals x squared. The width of each of the rectangles is going to be delta x, but because we're going to go break this down into an infinite number of subdivisions, we take this the calculus step further. Instead of saying delta x, which is a finite difference, we're going to talk about dx, which is our infinitesimal difference, our infinitely small difference between the two. So this is going to be my dx here. This is still my height. This is still my width. This is still my sum symbol right here. We're still adding up a bunch of heights times widths. We're still summing heights times widths, and we're doing this over an interval from 0 to 1. So the point is to me is that this diagram encapsulates every piece of information I need to be able to write what the integral is that I'm trying to compute that's equivalent to finding this area underneath the curve from 0 to 1 out here. So the x value is the parameter of interest. So I stated the width of my x bounds from 0 to 1, and I stated the equation in terms of x that I want to integrate over. In this case, the y equation in terms of x was x squared. It's my integrand. What we learned last semester was that integration is very close to being the exact inverse of differentiation. When we're looking to compute an integral, we're looking to compute an antiderivative. I'll talk about the tiny distinction between those two in a minute here. So I'm asking myself the question, I want to take the, or excuse me, I took the derivative of something and got x squared. What did I take the derivative of, right? So this is our anti-differentiation. Well, I know that when we take derivatives of polynomial terms, we always just adjust the power by 1. So derivatives reduce the power by 1. So it must be the case that integrals are going to increase our power by 1. So I'm thinking to myself, this should be something like an x cubed term here, because I know that x cubed stuff gets derivatives that are like x squared stuff. But I'm immediately guessing and checking in my head here, and I'm saying to myself, well, if I took the derivative of 3x, or excuse me, of x cubed, I'd be getting 3x squared, and I only want 1x squared as I have in my integrand up there. So it seems to me that it would only be appropriate for me to keep 1/3 of that result to get back there, right? So now I think about 1/3 x cubed, and if I take its derivative, I get exactly x squared. We're back to having the value that's inside of our integrand. So I've determined an antiderivative of x squared to be 1/3 x cubed. It is true that there are other antiderivatives. We're going to talk about that in a second. Just hold on to that one right here. But what we also learned last semester is we should be evaluating our antiderivative, our evaluation bar, and we're evaluating from the x value. Because this is dx, I know that 0 is an x value, and I know that 1 is an x value. So from the x value of 0 to the x value of 1. And the way that we evaluate these guys is by substituting in x equals 0 and subtracting off, substituting in x minus 1. This is really just like our final minus initial. This is how we compute differences out there. So this should be 1/3 times 1 cubed minus 1/3 times 0 cubed. Notice, by the way, that anytime you have constant multiples like this sitting out front when you're evaluating an integral, that really might as well have just floated along out front and let you actually do the math that might need to really be done on the inside separate. This just tells me now 1/3 of 1 minus 0. Certainly, we're getting exactly the same 1/3 we got 1 second ago when we did our exact Riemann sum. But doing this integral was quite a bit easier. We just had to come up with an antiderivative and evaluate the antiderivative at the upper bound of 1 and subtract off the lower bound of 0. So again, this diagram is important because what I managed to do here is draw a Riemann diagram that helps instruct what integration I should do. The best thing that happened here is that we didn't do a Riemann sum, and you should all be thrilled about that because computing Riemann sums is usually really hard. It's true that integrals are also usually going to be hard, but they're usually also going to be easier than doing the comparable sums. So our nice thing here is we drew a picture that represents how we're thinking of adding up those infinite number of sticks to represent it as an integral rather than representing it as a sum. We're going to draw another one of these pictures here in a minute that's going to be intensely useful for us to do something a little bit more complicated. So let's do this slightly differently. And I want to now redo this problem 2 times. But we're going to make it a little challenge here. And honestly, this part B is a little bit more of like what's coming up in section 5.4. Okay, it's coming up in one of our future sections here. This might even be like 6.1. That's okay. It doesn't matter. This is ideas that we've got to have here anyway. So this is a little bit me looking ahead, but again, I have a hard time teaching Riemann ideas without motivating them properly, and this is where my motivation is for caring about this here. So we're going to do part A first. It's going to be almost identical to what we just did. Then we're going to do part B, and I'm going to say it's going to be almost identical to what we just did, but you're going to feel like it's a little bit different here. So notice that the only difference here is I have extended our interval, so it's now from 0 to 2. All right. Instead of from 0 to 1. And I got really specific here. In the previous one, I was lazy and I just gave a bracketed interval 0, 1, and you just assumed that I meant x there because that's our default thing to do. Don't do that now, right? Now I'm talking about doing our Riemanns in y in our second example here, but I'm still giving you x intervals, so we're going to have to make sure that we're tracking the appropriate variables here. So let's do A first, because A is how we've normally been thinking about this, right? So the only thing that we've got to do different for part A is just extend our interval a little bit. I'm going to draw my minimal picture here, my basic general Riemann diagram. Okay, hang on. Let me just try that again. I just got a little skewed there. I noticed my handwriting's working out pretty good on my digital pad here, but my picture drawing is losing its touch there. So importantly now, we are now thinking of this endpoint out here being at 2. Since I know that this is the y equals x squared function, I know that this height out here is at, or I'll just mark this point, this is at 2, 4. This is sort of our corner point on our diagram, right? And we're interested now in finding this area that is underneath over here. So not much is going to change here. I'm still going to draw my general Riemann stick. Since I am interested in adding up my areas in terms of the x value changing, I am always going to draw a Riemann stick that has a width of delta x. That's super important for me here. This helps me understand that I want to add up a representative stick. There's an infinite number of these sticks from 0 to 2. They all have an infinitesimally narrow width. They all have a height according to the function x squared. So this diagram is what tells me to do 0 to 2. Okay, all right, sorry. Now the diagram tells me from 0 to 2, the function that we are integrating, all of the heights are defined by x squared. All the widths are defined by this delta x, but as we get infinitely many sticks, they get infinitesimally wide, so that becomes our dx. We integrate the x cubed and get our 1/3 x cubed. We integrate x squared to get 1/3 x cubed exactly as we did before. And now this one we're just going to evaluate from 0 to 2 instead of from 0 to 1. That's going to allow me to evaluate this as 1/3 2 cubed minus 0 cubed. And we'll see we're getting here 1/3 of 8 minus 0. And so 8/3 is what we're looking at for our final answer. So what I want to do now, hopefully that was good. If you're good with the previous one, this is the exact same. I literally just changed a 1 to a 2 and did the same problem. But now I want to mix this up. Now I want to say to you, what if I wanted to integrate with respect to y instead and still do this same problem? Well, this Riemann diagram is going to do the whole thing for me here. All right, so let's do this problem a second time. But let's do this in terms of y. So this is the first exciting thing I think I'm going to do in a video here. If you guys watch the refresher, great. I hope none of that was too brand new to you. If you're watching this, I'm hoping that you're already familiar, at least expecting me to be going over some of these things. But this one is our first kind of new idea here. So now what I'm saying to you is I want to do this same exact idea. I just want to think in terms of y values rather than thinking in terms of x values. So I want to kind of draw the same diagram, but everything that was x-based should now be y-based and vice versa. So here's the thing I'm thinking. My curve hasn't changed. It's still the same curve. Oh, let me make sure it's actually something that looks like a curve. Oh, come on. That was two different things. By the way, one of the other technological things I'm still feeling out right now is it's kind of nice for me to just do this in Microsoft Word because I can type a bunch of words in here and then write around them. But I know that Microsoft Word is a little bit more finicky. I have a general whiteboard, which is less finicky, but it's not as easy for me to write words in. So I might be going back and forth with this. If we find any good preference for one or the other, we can make that judgment. So I've got my same curve. This is still y equals x squared is my curve out here. But I'm going to mark a few more points of interest on this graph now. Before, what we were indicating is that 0 to 2 were the x values of interest. But I'm noticing now I'm asking us to think about this problem not in terms of x boundaries anymore. 0 to 2 was the x interval over which we traversed. But that's with the function y equals x squared. So now what I'm thinking to myself is, instead, what should the y bounds be? That would be equivalent to the x bounds of 0 to 2. Well, it looks like my y value that this corresponds with up here is actually a y value of 4, right? Because we're looking at this function y equals x squared, I know that when we square 2, we're actually going to do a y value of 4. So if I'm thinking of my x values going from 0 to 2, then that is equivalent with the y equals x squared function. My y value is going from 0 to 4. Hopefully that's all good right there. 0 squared is 0, 2 squared is 4. But I want to draw my Riemann stick a little different here, right? Because here's the thing I'm noticing. I want an integral that is going to go in terms of dy, right? I want a integral with respect to y that is going to define this area for me now. So a couple of things I'm thinking. Before, since this integral was with respect to x, we put our bounds of x values. This was x equals 0 to x equals 2 because this was dx. Down here, since we're now thinking about how our y values are changing, our y values need to span all the way from 0 to 4 for us to get all of the representative sticks that are out there. So I know that my integral here, because it is in terms of y, will go from 0 to 4. That's the full span of all the y values that I see in my region of interest. The different thing that we got to do now is think to ourselves, well, dy sounds that we're like talking about a change in height rather than a change in width like we'd been doing in the past. My new representative Riemann stick, therefore, should be this guy right there. This is my Riemann diagram in terms of y for this area underneath the curve y equals x squared from x equals 0 to x equals 2. You should notice that the height of this is now delta y. That delta y height is exactly our dy term over here. So what our job is to do is to figure out, what's this width over here? What is the width of each of our individual Riemann blocks here? And notice a really important thing. Because this is dx, I needed an expression in terms of x in my integrand. Therefore, because this is dy, I'm going to need an expression for y in my integrand here. Right? I need an x equals in terms of y rather than a y equals in terms of x. So one of the moves that we might be making over here is to solve this equation for x. We should be getting plus or minus y as our equation. But a small thing to notice here is that we are only looking at the first quadrant. We're not getting out any negative values here. We are interested in the area under this curve down to just the x-axis. So I'm going to go ahead and just keep the positive that's associated with this here. So this is really just telling me x equals root y is my alternate way of describing what curve I'm looking at, right? Y equals x squared and x equals root y are the exact same relation, at least in the first quadrant there. Right? So in terms of y now, I now have a function that I think is help describing to me where this endpoint is over here, right? That's always going to be at the location of root y. That's the location of the left point of my stick. The little bit of the tricky part here is that the right end point of the stick is always at 2 right here. And this is always at a distance of root y. So if I'm asking you, what is that overall distance right here? Then it seems like this distance should be 2 minus root y. This says to get your total width of this stick, it's the entire distance from 0 to 2, but take off however much. Yes, the width right here. It's all of the 0 to 2, but we want to chop off this root y distance right here. We want to chop off the x distance. X is the same as root y, and we want to remove the x distance that we've seen, or the root y distance that we've seen. So the width of this stick, and notice here, let's actually do another quick experiment. If y is 0, then we're sitting down here on the x-axis. And if y is 0, then 2 minus root y is 2 minus root 0, which is 2. And we do have a full width of 2. Our other extreme is that if our y value is all the way up at 4, then we're looking now at the stick that has been squashed down to no thickness whatsoever. And if y is 4, then the width of our stick is 2 minus root 4, which is 0, which is appropriate because our stick has been smashed all the way down there. Right? So this is certainly a more complicated one, but it seems to me like the width of all of our sticks is going to be 2 minus root y. And so it seems to me like this integral should be the same as the previous. It doesn't look the same at all. But based on my Riemann diagram, I'm now able to come up with an alternate representation for this area underneath the curve in terms of y values instead of in terms of x values. So now let's see if we can actually compute this here. So one really important thing that I know is that roots are not my friend when it comes to integration. So I'm going to go ahead and rewrite this guy based on some integral rules that we know. First thing I know is that we can separate integrals based on, ooh, I wrote some things out of order here. There we go. I can separate integrals over addition and subtraction. I can also factor out any constant multiples like positives or negatives. And it's typically beneficial to me to write fractional powers rather than actually writing radical symbols here. So now we can perform each of these integrals one by hand. The integral of 2. Remember that 2 is a constant. And what types of functions have constant slopes? Those should be lines. And so we are thinking, what function did I take the derivative of to get a constant? Well, a line. So this should be like 2y. Now, the derivative of 2y with respect to y is 2. So I'm going to get a 2y. And that's evaluated from y equals 0 to y equals 4. We're subtracting off of this guy. Now I've got to integrate y to the 1/2. And this is a little bit tricky right here, right? Just like the previous one, except even a little bit more so. So again, I know that when I'm doing a power rule with integration, that we should be thinking that derivatives reduce the power by 1. Therefore, integrals increase the power by 1. So I should increase the power by 1. So 1/2 goes to 3/2. But now I'm thinking to myself, if I were to take the derivative of this guy, I would get 3/2 y to the 1/2. And I only want 1 y to the 1/2. So I need a reciprocal coefficient to help cancel that stuff out. So a 2/3 right there. So notice now, if you take a derivative, the 3/2 will pop down and cancel with the 2/3. Subtract 1 from the power, and you get that power of 1/2, just like we originally had. So this guy also now looks like it's getting evaluated from y equals 4 to y equals 0. And so all we got to do is a little evaluating here, and we're done. The first one here, 2y, evaluated from 4 to 0. This is 2 times 4 minus 2 times 0. And so we're just getting 8 from our first piece. Minus our second piece over here is a little bit more going on with it. And our second piece here, I'm evaluating, I'm going to leave this 2/3 up front. And it looks like I've got a 4 to the 3/2 minus 0 to the 3/2. When I go ahead and evaluate this guy, I'm thinking to myself, doing these fractional powers right here, the thing I like to think to myself is, in this 4 to the 3/2, I don't know, you can do this with a calculator if you like, you should be able to do this in your heads. 4 to the 3/2, you can either do 4 cubed first, or you can do 4 to the 1/2 first. 4 to the 1/2 is easy for me. 4 to the 1/2 is the square root of 4, that's 2. So my inclination here is when I do 4 to the 3/2, I say that is do the square root first, so that becomes 2 cubed. 2 cubed will give me 8. So I'm going to go ahead and subtract off 2 cubed, or sorry, 2/3 of, and this is 8 minus 0. And so notice here, 8 minus 2/3 of 8 should just be 1/3 of 8. And that's going to leave us with 8/3. And you should notice that 8/3 here is our answer. Is exactly what we got when we did this in terms of x a minute ago. Right? So it does look like these match with each other right here. This is a little bit of a weird example in the sense that I think that the hardest part of this example is coming up with that 2 minus root y term right there. I expect that you guys could easily kind of flip things around in your head to think instead of y in terms of x, think x in terms of y. So getting x equals root y is our equation instead of y equals x squared. I think that's perfectly reasonable. Sometimes it's a little bit tougher to come up with what that width of that stick is. So maybe that 2 minus root y, that part is the harder part, but hopefully we can handle this integration right here. And again, kind of the purpose of this example is I am getting a little ahead of myself in terms of course content, but I really want to prove to you that Riemann diagrams matter. Riemann sums we might not keep on doing, but Riemann diagrams are going to be crazy helpful for you in figuring out what are your bounds of integration. Here it was 0 to 4. What is your integrand, and with what variable do you want to integrate with respect to? In this case right here, it was obvious that it's easier to do this problem in terms of x than in terms of y, but you had better believe that there's going to be some problems where it's going to be easier for you to convert to the other variable instead first. This one we made more work for ourselves by converting to y. That was just to illustrate a purpose and to match a previous example. So again, there's going to be plenty of scenarios in which the first step for you, rather than just plowing on into integration, is going to be to say to yourself, should I add up vertical Riemann sticks in terms of y, or should I add up horizontal Riemann sticks in terms of x? In either case, we're adding up a bunch of one-dimensional sticks to get a two-dimensional surface. One-dimensional sticks, and it got us a two-dimensional surface out there. So in either case, we're adding up an infinite number of one dimension lower objects and getting a one dimensional higher object that's out there, right? And so we got this 8/3 both ways. So this thing that we just did right here won't come up again until a couple more sections, but like this seems like a perfectly reasonable, and in fact, I kind of like this as a concept-based test question even. I can't believe I'm talking about test questions on day one, but I do like this conceptually to say, do a problem two different ways. Draw me the diagram that's associated with each of the possible concepts, because this proves to me not only do you know how to do integration, but it proves to me that you know how to think about integration. And one of my big goals as a professor, especially teaching online where it's a lot harder to like verify what we're doing, uh, yeah, great. I'll get to your question one second right there. Is to show me that you understand the concept and not just the action, right? So doing integration is different than knowing how to set up an integral. And honestly, you should expect a bunch of questions this semester. I mean, just straight up test questions that are just going to say, tell me what integral is associated with this picture. That's absolutely going to be a questions that you're going to get in Calc 2 and that you're going to get for the same exact reason in Calc 3 when you guys go to learn about double and triple integrals, which by the way are way easier than they sound like, but still it's going to say, here's a picture. Draw the integral that represents the area associated with this diagram right here. So the question that I'm seeing right now in chat is saying, can you do another example of getting the width or length? And I agree with the statement that you're asking right there. It's the other dimension, the non-dx or dy dimension right there with respect to y. And I'm going to say, yes, we're going to cover that in section 5.4. So that might actually come up more tomorrow. So the doing of that we'll talk about in its appropriate section. And so grave marks, I'll just say here, I think that the purpose of this is more of a motivating purpose than a be able to do this type of purpose right here. But again, I want to just emphasize that you guys should be able to think in terms of X and in terms of Y, because they're the same thing. They're just going in different directions out there. And so coming up with this right here, we'll do some more examples of this for sure when it's a specific concept. But I guess, again, I know I repeat myself a lot, but I'll say it one more time here. I want to distinguish in our minds Riemann sum from Riemann diagram. Riemann sums are a little unwieldy. Limits of Riemann sums are integrals. Riemann diagrams help us just know what the integral is. Rather than doing addition, we're doing calculus, right? So these diagrams won't go away. These Riemann sums, you should probably hope that these are going to go away. And they are going to go away until our last chapter of this class, when they're going to come back and kind of kick you in the mouth again here. But the concept of the diagram, this is really key for us early on right here. This will crop up a couple times, chapter 5, chapter 6. So, oh, and thank you, Grave Marks, and for claiming yourself right there, Max. And yeah, and again, I know that these, when I do this lecture on Twitch instead of Zoom, it's a little more one directional. I do kind of think that helps a little bit, but I very much appreciate it. If you guys, if I'm glossing over something, if I'm making a mistake, if I forget to turn my audio on again, stuff like that, I really appreciate you guys participating in chat. And also, I know you guys can't tell this, but where I'm looking at on my screen is immediately next to it is the chat. So if you guys say anything, it's hard for me to not notice immediately. So I do think I'll be kind of responsive to that. So there we go. So we've seen some Riemann actual computations, Riemann sums. We are seeing our Riemann diagrams right here, a little bit different, very conceptually helpful. I will absolutely ask you to draw some Riemann diagrams on a test. I will absolutely give you a Riemann diagram and say, tell me what integral is associated with this diagram, and vice versa. So this is a very important kind of picture that's associated with the first chunk of our class right here. So important Riemann ideas there. So let's kind of change gears a little bit. I guess the stuff that we talked about here that's important from these first sections is in 5.1, we talk all about our Riemann sums. That gives us our approximations, our L4s, our R4s. In 5.1, we take our limits and we get exact areas by taking limits of Riemann sums. In 5.2, we get into talking about our definite integrals. A definite integrals is where you know exactly the bounds. Indefinite integrals are where you don't know the bounds, are more generic statements of just tell me the antiderivative here. So let's just talk a little bit about that distinction. Let's talk through one other kind of representative physics problem using those indefinite integrals here. And that'll kind of be all I have for our 5.1, 5.2, 5.3. If you guys have other specific questions, I could probably kind of do some of those things too. But I didn't, honestly, my biggest takeaway, the most important thing for Calc 2 that you understand from 5.1, 5.2, 5.3 is the basics of how integrals are related to derivatives and the concept of a Riemann diagram and helping us draw a picture that represents the idea of an integral. So let's talk indefinite integrals here for a little bit. Indefinite integrals and the relationship between derivatives and integrals. I want to kind of remind us that when we did back in Calc 1, right, when you guys did all of your derivatives and stuff, we started by actually doing general or specific derivatives, right? We did things like find f prime of 3. And I'm assuming that on all of your first calculus tests, there's a lot of things like find the slope of this curve at x equals 3, find the derivative of or find the equation of the tangent line at x equals 5, stuff like that. And a typical breakdown, this doesn't happen in every class, but very often a lot of professors will kind of separate the definite derivatives from the indefinite derivatives, our derivative at a point from our general derivative, right? So this is this is sort of like our definite, and this is sort of like our indefinite. Was that we then said, okay, well, let's just find f prime of x in general. It should be an entire function of x, and you can evaluate it at any given x value to find the specific derivative at that location, right? So we kind of started to learn our limit definition of the derivative and all that. We did like our f primes of a and our f prime of 3, but then we said, listen, this could just be a whole function in its own right. Well, we're doing the exact same thing here. Our distinction here is we're going to switch from doing things like the integral from 0 to 3 of f of x dx to just being the integral of f of x dx, where we're not specifying an interval of values over which we are computing the or evaluating the antiderivative. We're just saying, in general, give me the antiderivative of this guy right here. So this is sort of our analogy, right? This is our differential calculus analogy. This is our integral calculus part of the analogy. This is just like we did derivatives at a point and then general derivatives. We are also doing definite integrals, intervals over a or integrals over a interval, or indefinite integrals, integrals not over an interval. These guys both just give us out whole other functions of x. These guys give us out specific numbers that we compute at the end of the day, right? This gives us a value. So our indefinite integrals are just asking us the question, go backwards, give me that indefinite integral. What did we take the derivative of to arrive in this situation? So now let me ask the question here. So now if we're looking for this more general antiderivative, right, we've still got our integral of x squared dx. We're still looking for what variable, or sorry, what function did we take the derivative of with respect to x to land at x squared? And we kind of already did this one, but there's a special addendum that's different to this now because we are in terms of an indefinite integral. We have not been given any bounds of integration. Now this is just the question, what is the antiderivative? And I asked that question in a technical sense a little wrong. And if you're listening there, I'm going to say it again. I just asked the question, what is the antiderivative? And if you're remembering from last semester, the answer is, well, there's not just one antiderivative, there's lots of them. The question that we're asking is, what function could I have taken the derivative of to get to x squared? We've already talked through our little guessing and checking here. Derivatives decrease the power by 1, so integrals should increase the power by 1. So I know I'm going to look at some form of x cubed. But I do my quick little constant multiple guess and checker for myself here. If I were to take the derivative right now, I'd end up at 3x squared. I only want 1x squared, so I only want to keep 1/3 of what I'll get out of that derivative. So 1/3 x cubed seems to be my little bit more appropriate antiderivative here. Now, again, I want to go back to my question. I want to ask, if I took the derivative of something and got x squared, what did I take the derivative of? And you might answer to me, oh, 1/3 x cubed. Because if I take the derivative of 1/3 x cubed, the 3 pops down, cancels with the 1/3, we get x squared, we're all good. But There's other parts that could be part of this as well. And so the thing that I want us to remember here is that this could be, instead, there could be parts that when we took the derivative, they went to 0, right? All of these seem like they might work. All of those are acceptable answers in a sense right here. If I say to you, what is the antiderivative of x squared? There's an infinite number of answers. And the reason is because all of these on the right, when you take the derivative, you get x squared back on the left. The reason is this constant out here, this constant, when we take its derivative, it just goes to 0, right? So that doesn't give us any more parts out here. So what we kind of saw, hopefully last semester, is that when we take our indefinite integrals. Oh wait, I dropped it. Okay, there we go. I'm dropping a part right there. That's a cubed right there. 1/3 x cubed. In general, we always will write these indefinite integral answers with a plus c on the end to indicate it could have been any of the infinite family of vertical shifts of that function. The picture that goes with this over here is this. Let me see. Oh man, I'm really setting myself up for it now. Okay. Hey, that wasn't too bad. So in all, okay, that last one got bad here. The point is, these are supposed to just be some like cubic function. And then the same cubic, maybe plus 1. And the same cubic, maybe plus 2, right? The point is that all of these functions, the derivative is the same. Notice that all of these functions have a derivative of 0 at that 1x value, if I would have drawn it right. They all have a derivative of 0 at that 1x value. The fact that they were all shifted up and down, shifts don't affect slopes, right? So no matter how steep you are, if I shift you up, you're still the exact same steepness. Your steepness is not affected by a vertical shift. Vertical shifts don't affect steepness at an x location. Okay? So therefore, any vertical shift may or may not have been incorporated into our antiderivative. We're not sure which of these functions we got back. We just know that it's any of these functions, family of functions, because they all follow the same pattern of slopes right here. They all have the same slope term if we were to take its derivative right there, because that constant of integration, when we take its derivative, goes to 0. It washes away to a meaningless thing there. So this plus c is really important. I'm going to look into my camera now and make my eyes all big and crazy. Don't forget your plus c's. And even now, I'm also going to say to you some even more things you got to be watching out for here. In your homework in My Open Math for 5-1-5-2-5-3, a lot of the problems in there, like I can make my own problems, but I can just like browse through other problems other people have made and select them, which I do for a bunch of problems. I make my own when I don't see what I'm looking for. And what I'm noticing is that some professors that have made problems for these things in there, they'll say, compute this indefinite integral. And what they will do is there'll be a little text box for you to type in, but there's plus c is already written afterwards, so you don't need to write it. There's other ones where the plus c is not included, and if you don't put a plus c, it will tell you that your answer is wrong because it matters. That plus c is super important. And I'm about to tell you exactly why it's important to us right now with an example. But again, this constant of integration always pops out when we do a definite integral. So just remember, if you ever compute an integral that doesn't have bounds, you had better have a plus c on the end in 100% of all cases out there. So let me say two small things about this, and we'll do this one last example that I want to do right here. My first question that I want to answer is, why don't we include plus c when we do our definite integrals? And the answer is, we actually do, we just don't see it. And here's what actually happens. If I were to do something, if I come over here, if I were to do the integral from like 1 to 3 of x cubed dx, then what I really, truly, honestly should be getting is 1 cubed, or what? Sorry, 1/3. Sorry, I'm trying to do the exact same problem right here. That's a squared right there. I'm going to get 1/3 x cubed plus c is my antiderivative, evaluated from x equals 1 to x equals 3. If I go ahead and evaluate my antiderivative at 3 minus evaluating my antiderivative at 1, I'm going to get 1/3 times 3 cubed plus c. There's my first grouping. That's the antiderivative at 3 minus the antiderivative at 1. That's 1/3 times 1 cubed plus c. And notice what's going to happen here is all we're going to be left with is just 1/3 times 3 cubed minus 1/3 times 1 cubed plus c minus c is going to cancel in 100% of all situations. There's no way that that could ever not happen in a definite integral. So in definite integrals, that plus c is always there under the hood, but 100% of all scenarios, the upper bound cancels with the lower bound's c because it's always going to be a plus c and a plus c and a minus in between them. And so nobody ever writes this. Like I've never seen anybody like incorporate these plus C's in here when they're evaluating these things. It's just we get to kind of in a sense discard that plus C. And in this case right here, it looks like we should be landing out for our final answer 9 minus 1/3. So what's that? 26 thirds is what we should be getting there from 1 to 3 for x squared, right? So, but importantly here, the point is plus c is sort of always there. We just get to ignore it in the definite integral because it will always cancel. In indefinite integrals, it basically needs to be there or you're wrong. We need to acknowledge that there are an infinite number of answers, and this is the infinite one parameter family of functions that represents all of the possible answers that it could have been. It could have been all of these graphs out here, any one of them, and we need more information to pin down which one. So what do we mean by need more information to pin down which one? Let's do some physics. I can say, so as I said in the, if you guys watched my like welcome video yesterday, one of the things that I said is I obviously love teaching the calculus classes. I haven't taught Calc 2 before, but again, I've taught Calc 1 a bunch, Calc 3 a bunch, DiffyQ a bunch. I know where you're at and where you're headed. One of the small things that I know that makes me a little bit sad about Calc 2 is it's probably the calculus class where we discuss physics the least. And whether you are a physics person or not is irrelevant. Calculus was invented to do physics. It turns out that calculus helps us do an unimaginable number of things outside the realm of physics now. But we didn't know that when it was like first being kind of discovered and kind of created as a tool. So the original purpose, the background behind calculus's existence was to answer physics questions. And so I really like to kind of keep that historical component with the class, and whether you're all physicists or not, or engineers is irrelevant. You just think of this as the historical component to the class then instead. So I like to kind of make sure the physics problems are in here, very especially in terms of position, velocity, and acceleration. So we will see some physics things this semester. I think it's just the lightest touching of it out of the 4 calculus courses. But that's okay. We're going to see tons of other great stuff this semester here. So here's, I think, a very reasonable problem. I think, honestly, this might have been on my like final exam for my calc students last fall. I'm not quite sure. But what I want to do here is talk about a little bit of our general, our indefinite integrals, and talk about our relationship between position, velocity, and acceleration. So first, let me write that position, velocity. I'm going to write these vertical of each other. So in general, these the variables used for these are either x or s. Velocity is pretty much always v. Acceleration is pretty much always a. I just want you guys to know there are entire textbook that only use s as position because they don't want to confuse it with a generic variable of x. And we'll talk about these things in time. Mostly all physics problems are in terms of t because we're talking always in terms of time. The thing that we learned that's very important in differential calculus is that since velocity is the rate of change of position, that means that the derivative of position is velocity. Very similarly, since acceleration is the rate of change of velocity, the derivative of velocity is acceleration. So another thing that we could say here is we can make a statement that says something like if, and I'll just use x because I use x, if x is position, then it should be that x prime, our derivative of x, is velocity. And it should be that the second derivative of time, the second derivative of position is the same as the first derivative of velocity, is the same thing as acceleration. Since we're now talking about integration, and we know that integrals and derivatives are essentially inverses of each other. Oh man, I forgot that little part. I'm going to run back to that at the very end here. That means to me that we should be able to do integration to go the other direction here. So notice the layout of my diagram and notice what we've been given and what we're being asked for. What we're being asked for is a final position. Our goal in this problem is to determine position information. What we've been given is we've been initially given acceleration information. So it looks like we're starting at the bottom of this column with acceleration, and we'd like to use that to determine position. So it seems to me like we want to do a couple integration steps to help lock our acceleration information into being position information back here. And it looks like we're going to have to talk about velocity along the way. Right? So this is a list of derivative relationships, but it should be the case then that there is a equivalent list of integral relationships right here. So another thing that I might think to myself is that if I'm going to take a derivative of velocity to get acceleration, then it should be the case that velocity is the integral of acceleration. I'm just flipping the nature of that relationship right there. Very similarly then, it should be that position, x of t, is going to be the integral of velocity. This is saying accumulate, and by the way, like even think about the units on this. Position is measured in meters. Over here, we're adding up a bunch of terms, and all the terms are velocity times time. Meters per second times seconds gives meters. Add up a lot of meters terms, you get meters. Over here, meters per second squared times seconds gives meters per second. And if you add up a bunch of meters per second terms, you're going to get meters per second in terms of velocity. We can just see our units over here. So we've got all these derivative and integral relationships between position, velocity, and acceleration. This is like one of those like things where I try to avoid doing like overly specific types of examples that I care for my students to know about, but like there is no better example for understanding derivatives and integrals than position, velocity, acceleration. Like that is just the cleanest sequential relationship that goes both directions. This is the easiest way to get your hands on our good concept information here. So in our case, this is going to be our guide for right now, because you should notice that we were originally given acceleration information. We should be able to use an integral to convert acceleration into velocity. We should be able to use an integral to convert velocity into position over here, and then we'll have an equation for position. Notice also, by the way, we want an equation for our final position. So I'm not looking to get an answer like 15 meters. I'm looking to get a whole equation in terms of time that's going to give us our answer here. So let's see if we can walk through these part by part right here. So our first piece of information that we were given is that our acceleration is 6 meters per second. So what I can do is I can start walking this information towards being position information by integrating. I can then say something like my velocity then should be just the integral of my acceleration. This is really simple because my acceleration is 6. It's a constant 6. So if I'm going to go ahead and compute this integral now, I am going to say, well, what do I take the derivative of to get the constant number 6? And the answer is 6t. That's what I would take the derivative of with respect to t to get 6, is 6t. But we can clearly see here that we are doing an indefinite integral. We do not have any bounds of integration. Nothing says here, what distance did we travel from time 2 to time 7? That would be a definite integral. Bounds have been given for time. This is just saying, give me an equation that gives position so that I could plug in the t's myself later. So since this is an indefinite integral, it matters that we go ahead and give ourselves our plus c out there on the end. But this is kind of problematic for us now, because what the heck am I supposed to do with that plus c out there? So right now, what I've kind of concluded from that first little bit of work is v of t equals 6t plus c. So that's kind of good, but it's kind of not helpful because I need a value for c. Well, as I promised you, we don't know which of these pictures we're looking at, right? And this idea right here, we just got a whole one parameter family. And what I would like to know is which one of these curves represent the one that pertains to our situation. So what I can do is I can come and use a little bit of our extra information. I'm being told that our initial velocity was negative 10 meters per second. A negative on velocity in our case here just means going to the left instead of going to the right, or going down instead of going up, right? So initial velocity, initial means at time 0. And so what this is telling me right here is this is telling me that we have an ordered pair of TV time velocity is 0, negative 10. That's an ordered pair that I know for time and for velocity here. So we can go ahead and apply that to our velocity situation down here and get an exact, instead of our entire one parameter family, get our particular solution to this integral based on an initial condition. So I know that v of 0 at our velocity at time 0 is negative 10. That's 6. Our time is 0 plus c. And so it looks to me like we're just getting a pretty simple c is negative 10. And so I now know that my general velocity equation associated with this particle is going to be 6t minus 10. So what we've done so far is we've stepped our acceleration information to being velocity information. Now we want to step our velocity information into being position information, and we can do that the exact same way. Because velocity is the derivative of position, we can integrate velocity to get back to position. We're taking the integral of a derivative to get back to the original function of position here. So now I want to say our position is the integral of velocity. And this is good because we have an equation for velocity. It's our 6t minus 10. And if we stop and do, oh my gosh, I'm forgetting my dt's right here. This is going to be one of those sad things about not being in a classroom. I usually assign a person to just be my representative detail tracker. I'm going to probably drop some things like those DTs and bounds of integration and some stuff. Those are important. Those are really important. So if you see them, call them out in chat. Don't you forget them. If I'm dropping them, that's because I'm being bad. Don't you follow my example there. Things like your DT, your DX, your DY, your bounds of integration. Those are critically important to being able to actually do any of this. Don't go leaving those guys off there. So we want to get an integral right here. Yeah, thanks, Grave. So integral of 6t first. Ooh, and by the way, I'm just going to write some stuff out differently here just to maybe, I don't know, write this a little bit different. I'm kind of hoping that we can just do this guy straight up in our heads. And so maybe I'll just write that guy right here. But don't forget that we can really break these things down based on our rules of integration here. This would be my most broken down way of writing this guy. I can separate this over addition and subtraction. I know I can factor out constant multiples. So this is really just 6 times the integral of t dt minus 10 integral dt. That's really, there's just a 1 that's in there, right, for that second integrand. Either way that you do this, we should be landing at a 3t squared. And again, stop and take a moment and convince yourself. I always do this pretty much by guess and check. I go backwards and then I go forwards. The derivative of this, the 2, would pop down to multiply to give a 6, and the power would become 1. So by checking, I'm convinced that I'm right. Similarly here, minus 10, well, we've done the integral of a constant. We just get that constant plus our integrand, or our constant of integration. Maybe I'll at least call this C2 so I make some sort of distinction because we've already had a C on this page. A lot of people, typically a C will get used if you're only ever going to have one constant of integration, but if you're going to start having several, people will typically switch to K and do K1, K2, K3, whatever. Pick something, be consistent so that you don't start confusing yourself. I don't care what you do. I care if you don't make mistakes based on bad consistency. Pick a system and do it all the time. And if you decide that your system makes you make dumb mistakes, change your system. Start thinking for yourself. Remember that, I think a lot of people get hung up in math that they think that notation was invented and you have to use it. Notation is just picked for whatever helps people the most. If there's notation that makes you do things differently, better, then that's the notation that you use now. So notation's for you. As long as I can interpret it, it's cool if you make up your own. Pick smart stuff that doesn't lead to confusion. If you have 6 different C's on one page of work, you're probably going to end up making a bunch of small, dumb mistakes. Don't do that to yourself. Pick a system, make it smart. So in any event, we're back in the same boat, right? We're now into a position equation right here. This is our x of t. But again, we now have a constant of integration. But again, we were given additional information. I knew that after 2 seconds, the particle has a position of 20 meters. This says to me, we really have the additional point associated with a function here, that the x value, sorry, I backed up real quick there. Turns out in this one right here, time is actually our input variable, and x, strangely enough, is our output. But x isn't that weird of an output if we think about it as a position in a physics equation. It's just, x just is usually our input variable, but it makes sense to predict position based on time. So in this case, we had the tx pair of 220. At time 2, position was 20. I can use this ordered pair to help me clean up my last equation here. And I think we're essentially good to go for the day then. So down here now I can wrap this up. I know that x of 2 is 20. And so my time of 2, we have 3 times 2 squared minus 10 times 2 plus C2. And we now have enough information to solve for C2, and we'll have a clean x equation at the end. I'm seeing here 20 equals, let's see, 12 minus 20 plus C2. This is a negative 8. I'm going to add negative 8 to the other side to get 28. And it looks like I've got a C2. And so it looks like now we've worked our way to our final equation right here. It looks like now I can claim that I do know a position equation for any time t. It looks like it's going to be our 3t squared minus 10t plus 28. So this is our good example of both indefinite integrals as well as initial conditions. Notice some small technicality here. In general, things like these two terms here are referred to as initial conditions. You should notice that they're called initial conditions because so often they're at an initial location. You should notice that technically this point here is not an actual initial condition. It's more of just like a condition at time 2. It wasn't a starting condition. That is usually when we say initial conditions, we just mean like conditions. They're often at 0, but often I'll also give ones that aren't quite at 0, like that 2 right there. So I refer to this as an initial value problem or an initial condition problem. It's where integration is required, but since that integration is always going to give us some undetermined parameters of c and c2 here, we needed extra pieces of information to pin down what value those parameters should take on. Graphically speaking, we're thinking that the integral provides us an infinite number of possible graphs. We want to pick out which one graph relates to our scenario by getting one extra point on that graph. By knowing, for example, that we had time like 220, might have said like, oh, it's that graph. Maybe there's the one graph that has 220 on it. So we've pinned down an infinite family down to the one choice that fits the rest of our information there. So here's my example of doing some definite integrals because we were not given any bounds over which to integrate, an interval of times over which to integrate. We did general integrals that gave us plus c's. We can always solve for these constants of integration if we're given additional pieces of information, which are often called initial conditions, whether they're truly initial or not. Maybe my only other final thing there is sometimes people say my initial velocity is negative 10. Realize that that means that 0 is being implied, told to you right there. Like that means at time 0, the velocity was negative 10 right there. So initial means times 0 if nothing else is ever explicitly stated like that. I only have one last thing to say right here. It's really just something I kind of accidentally glossed over up here. And that is, and what is the relationship between our derivatives and our integrals? What we have stated multiple times here today is that derivatives and integrals are essentially opposites of each other. When I say opposites, I mean inverses of each other. But we do want to see one technicality that makes that not 100% true. And it comes back to our constant of integration here. So I'm thinking to myself things like, if I start with like x squared and I integrate, then I'm going to get 1/3 x cubed plus c. And if I then take the derivative back, then now I just get back to x squared. And so we're like, hey, cool, taking the integral, then the derivative returned us back to our original function. Therefore, integrals and derivatives are inverses of each other. But we got to be a little bit more careful here. What you should have learned in algebra is that it's not good enough for f of f inverse of x to give you x to call this thing an inverse. It also needs to go the other way. It also needs to be that f inverse of f of x is also going to give us x. And so we come back over here and we ask the same questions. And I say, okay, well, x squared, if I go ahead and derivative this guy first, then now I'm going to get to 2x. If I integrate, do I get back to x squared? Ooh, and the answer is almost. I really get back to the entire family of functions, x squared plus c. So you should notice here, this is not quite a perfect inverse because we started at x squared and we got back to x squared being one of the possible solutions, right? This is one function. This is an infinite number of functions, one for every single value that c could possibly take on. So notice here that we almost, but don't quite get this whole f inverse of f of x is not quite equal to x. And it is super close. I'm saying not equal. It is really close. So this is one of those things where, like, on the one hand, it's crazy useful for you to always think to yourself, yeah, integration, you just do the backwards thing of derivatives. Like, they're inverses of each other. That's a great concept for you to always have. It's always going to help you to think that. On the other hand, if you walk into future calculus classes and you say to your professor, yeah, it's cool, I know that derivatives and and integrals are inverses, then the guy's going to look at you and be like, all right, there's a C student. Don't go overstating what you actually think that you know here. Remember that there's always this slight discrepancy that make these not perfect inverses of each other. Going one direction, we get perfect inverses, but going the other, that plus C term ends up cropping up right there. And it's essentially because we lost a little bit of information when we computed the derivative, and we attempted to reclaim that information when we took the integral, but all we said was, well, it was one of these choices. We're not sure what information we lost. Notice that this problem would have been the same, the second one down here, if I had started with x squared plus 7, right? Then we would have got to 2x, and then to x squared plus c. We lose track. We lost a piece of information. So there is a little bit of information loss when we take derivatives. But not so much when we compute integrals. And that's one of the reasons why these aren't perfect inverses of each other, but they're super close. It's the plus c that ruins them being perfect inverses of each other. So again, my summarizing statement there is it's very helpful to think of derivatives and integrals as inverses. It's also the case that if you want to look smart in front of other math people, you'll be able to explain why they're not quite perfect inverses. There is a little technicality that goes with that. So this is sort of what I kind of view as the highlights of 5.1, 5.2, 5.3, making sure you conceptually understand Riemann ideas, making sure that we can compute some integrals and derivatives, both definite and indefinite, making sure that we understand why the plus c is there when we do indefinite integrals, understanding why the plus c does not need to be included when we do definite integrals because it just cancels away. And understanding that it's helpful for us to kind of build sequences of relationships for ourselves, like we do with position, velocity, acceleration, understanding that each of them is one mathematical step away from each other in terms of the appropriate derivative or integral that we can identify. And that given initial conditions, we can always solve for some of these constants of integration here. So I think this basically gets at what I think are and again, there's some other really important things in 5.1, 5.2, 5.3. I just think they're all like easy things, like area above the x-axis is going to be counted as positive area, and area below the x-axis is going to be counted as negative area. I think those things kind of make sense. If your heights are negative and your widths are positive, then height times width gave you a negative thing. It's weird for us to think of negative areas, but it helps when we think of area as like a distance traveled. Now negative area really just means distance is left instead of distance is right. So as long as you don't get too hung up on what does -6 square feet mean, computing integrals and getting negatives for areas is not unreasonable. There are some other things that obviously are happening here in 5.1, 5.2, 5.3. But again, I think some of those things are the easier things that don't necessarily require me to explain some important fine details of. So my plan for tomorrow is to talk a little 5.4. 5.4 is really not actually even going to be 5.4 and 5.5. 5.4 is not going to be too super crazy. I think that basically what 5.4 is going to get at is we're going to see a couple more pictures like the early thing that we did. I think that we're going to see a little bit of stuff that looks like this, although this more formally really comes up in chapter 6, but we're going to want to draw some more really careful pictures tomorrow for 5.4. And then 5.5 is a great section. It's also our only other section that we cover in chapter 5 here. We're not going to do 5.6. 5.6 gets... 5.6 is a bunch of hard work for things that aren't really as valuable to us as the amount of work that goes into them. It never ends up quite being as valuable as the amount of time it costs us. But 5.5 is maybe the single most important integration rule that there is. 5.5 is the substitution rule. It is going to help us undo the chain rule. Chain rule is probably the most important derivative rule that there is, so hopefully it's not terribly surprising that the undoing rule associated with the integrals is going to be one of the most important integral rules that we'll get here. It's not too complicated, but it does require a little bit of notational finesse. So I do think it's helpful to kind of see some of that stuff. So tomorrow I'm going to hit some 5-4, 5-5 stuff. I think that this week we can handle just doing 3 lectures this week. In general, if there's other weeks where we need to extend and grab a third lecture, that really might happen. Obviously, some of this stuff's going to get a little bit harder here. If that ever happens, I'm planning on just doing it at the same time then on Wednesdays. You guys are still not going to be required to be here for them, so I don't think it should matter too much. I did a smart job of leaving my Wednesday time slot at this time open. It doesn't like have an office hour or something like that. I said I did a smart job. It totally happened by accident, but I'm pretty happy about it. But in any event, I think this week I'm good to go with just one more lecture tomorrow, especially if I let these drag out to be like an hour and a half instead of an hour. But again, in some future weeks, we might have a third lecture on that week. It'll just happen on the same time slot on Wednesday. So this 12:30 to approximately 1:30 is what I hope to reach for here each of these times. So that's what I got for you today. Tomorrow we're looking at 5-4 at 12:30 and 5-5. We'll get our doing our U sub, undoing some of those. And again, remember that you should be doing the reading beforehand with these. I'm gonna skip the easy examples for the most part. I won't be able to help it. I'm going to do one easy example, especially from 5-5. But my point for these is to try and only focus on the harder stuff or the most important stuff in a sense during these. So keep doing your reading beforehand. Keep writing out the examples that you're seeing in the reading. But for example, I'm planning on really just kind of picking some homework problems to essentially do specifically for 5-5 tomorrow. So make sure that you've done the reading before you're hitting up these lectures here. And yeah, I think we're good to go there. So I'm gonna conclude this stream right here. Get this video downloaded and posted in Canvas for everybody that wasn't here. And I appreciate those of you that were here live. That's nice. Continue to hit me up in chat. Grave Marks, I appreciate that. Maxwell, I could probably do your real names or your Twitch names. I understand the idea of a Twitch name here. Reading those off as well. So. Yeah, stay in touch with me, guys. Go ahead and keep looking at your homework. Remember, in Canvas, and by the way, maybe I'll just pop over here super quick. In Canvas, you guys should be heading to your, go to Canvas. In Canvas, you should be walking through your introductory assignments. You should have the 3 assignments that are sort of like not actually math. You should have your review assignment for 5-1 through 5-3. There should be some small assignments, each for 5-4 and 5-5. The deadlines for all these things are posted. So again, when you go to our Canvas page, this should come up as the default page. It might be more convenient for you to pop over to modules instead. However, in modules, we do have all the course information posted here. But importantly, there is also just the week 1 guide. It's going to have your guide, your introduction, your refresher, the videos. The videos I'm going to post are going to be in right here right now. So use the modules view here to help yourself, remind yourself where your stuff is at and what you need to be doing for the week. Yeah, again, stay in touch with me. I'm happy to answer any questions you guys have to kind of get integrated into the course here, no pun intended. So yeah, good one today. Happy Monday. Welcome to the first day of the semester. We'll do this again tomorrow, same time. I'll see you guys then.